So as I said on the previous page, these two types of errors are given really fancy names, so type 1 error and type 2 error. So type 1 error is rejecting the null hypothesis, so h sub 0 when h sub 0, the null hypothesis is true. And type 2 error is when we fail, so this is failing to reject the null hypothesis, h sub 0, when that hypothesis h sub 0 is actually false. Alright, now we just did this chapter on probability because again, it's what's going to help make our guesses educated, and it is what measures the probability also of making these types of errors. So we can measure the chance of each of these occurring, and so these are also given symbols. So type 1, type 2, so in numeric order 1, 2, alpha and beta, so A and B in alphabetical order. So alpha is going to be the probability of making a type 1 error. So again, this is the probability of rejecting HO when HO in fact is true. And beta is the probability of making a type 2 error. So this is the probability of failing to reject HO when in fact H sub 0 is false. Alright, so of these two, the one here that we're going to mainly focus on is alpha. And alpha is given a special name called the level of significance for a hypothesis test. And it is this thing that's going to be used as a cutoff between unusual and not so unusual results. So as we compute a probability can be any number between 0 and 1. And this value of alpha, if events have a probability less than or equal to alpha, this is where we're going to reject the null hypothesis. And in here, we're going to fail to reject the null hypothesis. Okay, so we're going to reject the null hypothesis if this p-value is less than or equal to alpha. Okay? So if that tail probability is less than or equal to some cutoff number like we used in the past, like 0.05, and we're going to fail to reject if that p-value, that tail probability, is bigger than alpha. So in a hypothesis testing procedure, the researcher determines a value of alpha that they can live with the consequences of if the sample data leads them to an incorrect conclusion. So in this class, the value of alpha will always be given. And if for some reason there's some problem where they forgot to do so, we're just going to use the previous value that we have used in the previous chapters of 0.05. So in the last chapter, you had some homework problems where you were actually doing a hypothesis test, or at least some pieces of it. We just didn't have names for all of the parts yet. Okay, so the table below maps out the thought process we started looking at in the last chapter in the first row, and in the second row it's going to give us the corresponding formal terms from hypothesis testing that we see in this particular chapter. Okay. So in the last section, we would compute something like the probability, like we'd be asked if some value of x bar was unusually low, and so we would compute the probability of getting an x bar less than or equal to that given value, and then we would see if it came out to be less than or equal to 0.05. Well, this probability piece is a tail probability, so that has been given a name now. That is called a p-value. And this 0.5 that we compared to in the previous sections now also has a name. That is our level of significance, which is alpha. So now we're really checking if that p-value is less than or equal to alpha. And then if this occurred, we would say x bar was unusually low if the claimed value of mu is correct. So we decided that mu was incorrect. So in this case, we rejected whatever their claimed value was. So the new terminology for that is we would reject HO where HO would say something like mu equals, and we'd have some specified number here. And then if we rejected and said we didn't think that mean was correct, that means we think that the mean value had changed somehow. And in this case, since it was unusually low, we would then conclude that mu was less than claimed. Okay, so in this case, that's what the alternative would have said. Mu is less than some claimed value. And so we rejected HO, and so now we're going to say there is significant evidence to conclude H sub A. Okay. So all of these steps that we were looking at in the last chapter dealing with these unusual values, we were really computing tail probabilities that were p-values. We were comparing to 0.05, which is really just a special value of alpha or level of significance. When unusual things happen, we said we don't believe the claim about the parameter anymore. And then depending on if it was unusually low or unusually high, we would then conclude that the mean had shifted in that direction. All right, so now it's time to go back to the example that we've walked through a lot of videos and a lot of steps and a lot of pages for, to kind of organize all of that and put it together in what we call a formal hypothesis testing procedure. Now these formal tests have a lot of steps that we have there actually is no new material here. We're just taking everything that we've done in these first 6 chapters and bringing it all together now. So this acronym PHANTOMS will help you remember all the parts you need in a formal hypothesis test. So initially we need to know what parameter we're dealing with. So P for parameter, we're going to set up a pair of hypotheses. So H is going to stand for your hypotheses. There are always some assumptions we have to check before we go ahead and use some sort of like normal CDF like we just used to compute the probability. Once those assumptions are met, we're going to actually name the tests that we're going to then use to compute that p-value. And then from there, we're going to have a test statistic computed from the sample data. We're going to obtain a p-value, that probability, that tail probability. Okay, and once we have that probability value, p-value, we can then make a decision about HO, whether we're going to reject it or not. And then finally, we need to state that conclusion back in the context of the problem. Okay. All right, so now we're just going to basically take everything that we've already accumulated in these last few pages and now put it all together in a formal hypothesis. All right, so the step 1 here would be to state the random variable and the parameter. So P from the PHANTOMS acronym up here for parameter. And so our parameter here, mu, was the mean lifetime of all XJ35 batteries. And now we don't know that value, but we get information for this value from X bar. So the random variable X bar is used here, so this would be the mean lifetime. And now we can actually fill in what that sample size was of 30 randomly selected XJ35 batteries. All right, our next letter is H for hypotheses, so we're going to set up the null and alternative hypotheses that we had earlier. So they claim mu is 500 days. We believe mu is less than 500 days. So we're going to test this hypothesis, and as our cutoff for unusual values, we were told up here to use a 0.10 level of significance. So alpha is 0.010. So again, level of significance, that is alpha.